we have a talk on software transactional memory. I think I said that right, transactional. Okay, but first just a couple of things. We'll have question time at the end. And for question time, what I'll need you to do is put your hand up really high in the air and keep it up, because I'll have to run over to you with the microphone so that we get your question recorded on our recording software up there. So just wait for me and just keep your hand up until I pass you the microphone. Otherwise, I might not be sure if it was you or the person sitting next to you. And okay, so I'm about to hand over to Dave. Dave is currently working for a trading firm in Chicago doing super fast things to the stock market. And he's also working on a PhD in computer science at the University of Minnesota. So he's a busy person, so thank you for having the time to come and talk to us. In the past, he was a long-time IBMer working in the Linux Technology Center. So again, thank you for coming to talk to us.
Thanks. So the original title of, actually there's part of that missing, just to show what happened when you do things in Emacs. The original title of this was Software Transactional Memory in GCC 4.7. They added those keywords into the language in 4.7. But it turns out there's been quite a lot of also other interesting things happening in transactional memory since I submitted the talk. Intel has, in their Haswell architecture, is going to add hardware support for transactional memory. Power 8 is going to have support for transactional memory. A bunch of other languages like Clojure and Scala have transactional memory support. So there's a lot of things going on. So I'm going to try and touch on most of that in this particular talk, though it was kind of initially motivated by the fact that it's in GCC 4.7 and nobody knows what the hell it is. So that was really the fundamental motivation for this particular thing. So one of the sort of rhetorical skills as a public speaker is to say incredibly obvious things with great profundity. So concurrency is important, and that's come up again and again in talks at the conference. My iPhone, I think, is up to 4 cores, and all the graphs that show CPU speed are leveling off. So how do we make things go faster? We run more and more things in parallel. So concurrency clearly is important. Concurrency is hard. It's difficult to, there's some very basic things. You want to add stuff to a linked list, throw a lock around it, thanks, that's great. If you want to start in parallel adding things to a linked list, it gets a lot harder. So concurrency is difficult. I've spent a lot of time working in the kernel. I mean, I do spin locks without thinking, but even so, I still screw it up frequently, right? You deadlock because you do locks in the wrong order. You forget to unlock. So there's all sorts of ways that using the traditional POSIX stuff is tricky. So transactional memory is a different approach. How do we do concurrency better? There's traditional locks. Lots of people use that. They've worked well. I mean, the whole kernel is based around a traditional locking model or kind of atomic operations. One of the other approaches that's very big in all the functional programming guys is the sort of shared nothing model. And I've used Erlang. The basic assumption is I will never share memory with you. I'm going to send everything back and forth in messages. I rely on the Erlang virtual machine to be smart enough that it doesn't actually pick up and copy everything when I send it around. But from a programming model point of view, I just do shared nothing. Both of those two things work. But transactional memory is another approach. Now, one of the sort of canonical cases for using transactional memory is inserting things into a red-black tree. So a red-black tree, so when you put things in a red, by the way, the most fun I had doing this talk, in fact, I spent relatively little time doing the slides. I spent lots of time building this animation, which was really cool. A red-black tree is sort of interesting because sometimes you can do things that just affect one part of the tree. And so these things, if I had somebody inserting things over at the left, it would work just fine. Other times, all of a sudden, the whole tree goes and rearranges itself as I'm inserting things into the tree. But putting things into a red-black tree is a really good example of where I would like to be able to do it concurrently. Right? Let's just say I'm taking words, I don't know, I'm Google building searches, for example. I've got a whole bunch of words coming at me. I want to put them in a tree so I can organize them. I'd really like to be able to put things in a tree concurrently, having 2, 3, 4, 100 threads all inserting into this particular tree at the same time. Well, today, the basic way everybody manages concurrency in a tree is you put a big lock at the top. I mean, that's really the only way people have. It doesn't work with the shared nothing model. There are deep academic papers that talk about techniques for doing locks at lower levels. They're incredibly, I mean, nobody will ever, first off, getting a red-black tree right in the first place is tricky. Getting one right where you're going to have locks at different levels, and they do reservations. So as I work my way down the tree, I add a reservation to this part of the tree, and then when I actually decide I want to do things, I might use that reservation. Horribly complicated. So I'm going to use the example of transactional memory through this talk to kind of illustrate and motivate why transactional memory is interesting. So this is code that will compile under GCC 4.7. In this particular case, it was moving things from one list to another. Take a couple of pointers to lists into my little function. And all I do is I add this keyword, underbar, transaction atomic with curly braces. Everything inside those curly braces, the compiler and the runtime assumes that I'm not going to conflict with anybody else. It just goes ahead and does it. But it keeps track of what memory I'm reading and writing. If anybody else goes and touches those pieces of memory while I'm touching them in a way that conflicts, right? Two people reading, great, you're good to go. But I read something in my transaction and then write something, somebody else writes to the same area, all of a sudden, oops, we have a conflict. The runtime notices that there's a conflict and rolls one of the two threads back. All the changes to memory that they made, it undoes. So it has to keep track of everything within these braces of all the modifications to memory that went on, because there might be an oops where I have to undo them all. Okay? So that's fundamentally how transactional memory works. It's just like kind of ACID. Actually, it's ACID without the D. Okay? Atomic, consistent, isolated and durable. Anyway, without the durable part because it's RAM. So sorry. But it basically says everybody is going to, the programs will all execute as if nobody else was executing, and the runtime keeps track of rolling that back. Okay, so that's fundamentally the way transactional memory works. So either everything that happens within those curly braces happens or nothing does. We've added essentially first-class language support to C. Now, I said that GCC added this in 4.7. There's a bunch of companies, Intel, Oracle, Red Hat, IBM, who are all sort of working on the standard for this language. So there is a published proposal for modifications to the language. Now, I don't know how many of you work with the sort of language standards bodies, but it takes decades to get, like if you're into C++, C++11, they called C++ 0x for a long time because they didn't know what year it was going to be. They did 0x because they assumed it was going to be in the 2000s somewhere, and they even got that wrong because it turned out to be 2011. So they should have done C++ XX because they were wrong even in the decade. So when will this actually become in the language? Not sure. But it's in GCC now. Intel has a prototype compiler that has the support in it. And I'm going to talk about the fact they're adding it to their hardware. And then Clang is not in the Clang base, but there's a bunch of people who have projects to do software transactional memory in Clang. It's in GCC 4.7. And one of the things is, you compare it to some other approaches for increasing concurrency. OpenMP is another one that's in GCC, right? There's OpenMP, almost nobody's played. How many people here have played with OpenMP? Okay, a few people. OpenMP is a more process-oriented approach to parallelism, or actually say, hey, I want to do this thing and fan it out a bunch of different ways and do it. Transactional memory is a data-oriented approach to concurrency because it basically says the language has really no idea how many threads you're running or how you started them or when you're starting them or when they're going to stop. All it cares is within this transaction, if somebody else goes and pokes at the memory that I'm looking at, we're going to manage that. One of the analogies I like is that transactional memory versus locks is like stoplights versus roundabouts. Okay? So the way a stoplight works is all the people who want to go this way get to go, all the people who want to go this way get stopped. So these guys have the lock, everybody over here, oops. No forward progress until the lights change, until they get the lock. The idea of transactional memory is everybody makes forward progress. And only if you get a collision, do you stop and do something. So, but in a perfect world, with a roundabout, the idea with a roundabout is nobody stops dead, everybody flows through, and life is glorious. Okay, maybe a better analogy, way to describe that is some people may have to slow down, but in general, everybody's making forward progress all the time. So that's the analogy, one of my analogies for transactional memory. So the term it's used is you make optimistic progress, locks are pessimistic So pick my red-black tree case. I'm pessimistic about somebody else wanting to update the tree at the same time. I grab a lock for the whole tree. I'm pessimistic, and I put my nodes in the tree, and then I unlock it. Maybe I was going to insert value 1,000,000, and they were going to insert value 1. So we were going to be in complete opposite ends of the tree, and we'd never touch each other's stuff. But locks are pessimistic. I say, just on the off case, we're going to step on each other, let's lock. Transactional memory is optimistic. We say, let's make forward progress, and only if we actually turn out to step on each other, are we going to do something about it. The other thing that's cool is it's fine-grained. And actually, when I talk about Intel has done some super cool things in there, what they've proposed for the hardware. By fine-grained, it means I may take a lock. Pick another example. I'm doing the standard Comp Sci 101. A structure involves people, with names and addresses and other stuff. And again, traditionally, if I want to update a person, I take a lock around the person. I update my things. I undo the lock around the person structure. Well, that's fairly coarse-grained. It's everything to do with the person structure. The transactional memory is fine-grained in that it's really only the specific bytes that get changed, where if a conflict occurs, I'm going to do something about it. So if somebody is updating the phone number and somebody else is updating the email address, to give kind of a stupid example, there's no conflict. Life goes on. Everybody's happy. In the hardware, by the way, that happens at a cache line level, so it's maybe slightly less granular than you'd want. But in the software version, it's actually at the word level, so 4-byte granularity. So as long as I don't conflict on a 4-byte boundary, I'm good to go. And it is a simpler programming model. And I got a few points about that later. Why should you guys care? Well, what's interesting about software transactional memory right now is this is the early days, right? This is a sort of interesting time where people are trying to figure out how to implement it, how to exploit it. Again, hardware support is coming in 2013, 2014. So I'll talk towards the end about the implementation in GCC, which generally sucks badly. So there's lots of opportunity to actually get involved and figure out how this should work and how to make it better. One of the things that people often ask, if those of you are involved in sort of open source development is, somebody comes up, some student or whatever comes up and says, I'd like to get involved in open source. How should I do it? And you're like, well, find something to work. You got to find something that interests you and something that's worth working on, and then start noodling in, scratching that itch, and doing something about it. Well, let me tell you, there is so much low-hanging fruit in terms of the implementation of software transactional memory in GCC that if you were to, somebody just come up and say, what kind of project should I get involved in? Well, here's one that, it's fairly easy to find things that could use some improvement. It is really growing. Again, the fact that it's all done in software right now means, and I've got some performance charts at the end, the performance of it today is not great. Great model, fabulous model. Conceptually, it's a great model. It's wonderful. Doesn't perform so well. So, but once we can start moving things down into the hardware, all of a sudden this is going to become more interesting. Better programming model, first-class language support, and it's really another tool in the concurrency toolbox. So, disadvantages of transactional memory. The cost of a collision, can be significant. I've gone and done a bunch of work, and all of a sudden it's like, crap, I have to undo all that work. I've spent a bunch of CPU cycles and memory bandwidth and everything else updating a bunch of things in my tree, and then all, the case where I had to rotate the whole red-black tree to the left, and then all of a sudden some dork who just inserted one node over here conflicts with me, and we roll the whole damn thing back. As a sort of aside, in the academic papers, there's all sorts of algorithms for deciding who you should roll back. Do you roll back the guy who's got the most work done, so maybe the guy who started earlier? Do you roll back? Anyway, lots of different choices for how to roll back. There's overhead in transaction monitoring. So I said that within a transaction, the runtime has to keep track of, and it's a combination, by the way, you'll see in a minute, of code generated by the compiler and a runtime library. They keep track of all the memory accesses that happen inside a transaction. So I've been playing around with a bunch of different benchmarks, and there's one benchmark that really did badly for transactional memory. And when you actually drilled down deep inside it, they actually were calling a Q-sort, a whole range of data inside a transaction. Okay? Well, we're talking like 1,000 nodes, we're going to sort them, and they're doing that inside a transaction. Well, while you're doing that, the runtime's like, oh crap, he touched this memory. Oh crap, he touched that memory. You know, read, write, you know, building up this enormous cache of all the things that have changed, so it can roll it back and by the way, both detect conflicts with other transactions and roll it back if you need to. And so that did a lot of overhead there. So if we're only talking about I'm going to do a little transaction, I mean, like say spin locks, right? I mean, you want to do relatively little things into spin lock. If you want to do little things in a transaction, that's pretty good. Once it starts growing, there's overhead there. It can be really difficult to debug transactional memory. The reason I got into looking at the GCC, I've been a kernel guy before, I've never had to look at the GCC source code. The reason I got into that is there was actually some bugs where, in the compiler, where they hadn't tracked every read and write. So you'd wrap, as a developer, you'd wrap your code in curly braces, inside Transaction Atomic, and assume that the compiler was going to do the right thing, and it wasn't. Well, how do you, a little tricky to track that down. The other classic case is, and this is exactly like any other locking mechanism, I decided that this particular data structure, my student structure, or person structure I talked about before, I'm going to treat transactionally because I've got lots of threads touching it. Wonderful. Well, one place in the code, let's just say I forget to do transaction atomic curly brace, right? I just put the code in there. Oops. I mean, there's nothing that's going to warn you that you forgot to do that. It's just there's going to be some incredibly subtle bugs where your students are getting corrupted. Now that's not any different than standard pthread lock problems where I forgot to put a lock around something. But it's tricky to debug. And that was the last bullet there. Sorry.
Yeah, would that be easier to keep like with a Valgrind plugin? So you just set a bit per thing that it was done under a transaction. So if you have access to that, then you're.
So the question is, could we have something like a Valgrind plugin that would keep track of the things that are done in transactions? And that actually falls exactly into my example of there's so much low-hanging fruit around STM support right now that, debug. How are we going to debug this? One of the other ones, I'll talk about it in a bit, is you can actually, it's relatively easy to replace the runtime library that the compiler is going to call to track the transaction. So you can do all sorts of cool instrumentation or decide your algorithm is going to be better or whatever. One of the other ones is, my application's running really slow, tell me which transaction I was spending an awful lot of time in. Well, so I actually done a little bit of playing around with, I'm going to track the start time and end time of a transaction, and then I can dump out at the end to say, this transaction invoked on this line number, took this amount of time on average, this transaction on that line number took this amount of time on average. It's like, oh crap, I should go see what I'm doing in that transaction. So between Valgrind, between instrumenting the library, there are lots of the world of things you could do to make this more viable is enormous. The worlds of things that have been done to make this more viable is actually it's non-existent. So there were some, when I talked about the, so I mentioned the idea that this is a better programming model a couple of times. What makes it better? One is there's actually no possibility of deadlock with STM. Everybody supports nested transactions just fine. And if I can nest transactions as deep as I want, that's just fine. So there's no possibility of deadlock, which is cool. Second thing is, if you return in the middle of a function, the compiler actually notices that I'm leaving that scope, right? The way I coded it was I said transaction atomic curly brace. Compiler says, ooh, he's leaving the scope of that curly brace. I better, I can end the transaction. I can do whatever. So it, the classic case of the reason there's gotos in the kernel, not totally true, but the reason there's gotos in the kernel is because you unlock things when you leave your routine, and so everybody goes to the bottom and then unlocks. You don't have to scatter unlock all the way through your code. The compiler takes care of that for you. It's very similar to a lot of the object-oriented kind of C++ or Java, where you can actually do the term is resource acquisition is initialization, right? You grab a lock by creating an object, and when that object leaves scope, it unlocks it, and then it's a much simpler model. And again, the compiler figures out what's conflicting, right? I don't have, it figures out where the conflicts are. I don't really have to figure out what I need to lock and unlock. So let me talk briefly, just for like one slide, I think, about software transactional memory in the Java languages. There's a couple of pages out there. CCSTM is a Scala thing. Actually, I think this other one's a Scala link as well. There's a whole bunch of Scala support for transactional memory. Now, I'm a C kernel guy, so anything that runs on top of a JVM is like, what the best terminology for that I think was everything that runs in that kind of environment is really just a test case for the kernel. So I consider that way too high level. It's actually way easier to do transactions when I can manage objects, right? When I'm running in a JVM environment, I can take a snapshot of a whole object, and copy it off somewhere, and then detect conflicts that way. The whole doing it in C, which is what one of the terms is an unmanaged memory model, where I can manufacture a pointer, right? I can add some hex bits together and manufacture a pointer, reach over there and touch that. Managing transactional memory in that world is a lot trickier than in an object-oriented model. So there is lots of support. I think it's easier in the object model, and I actually don't really give a damn. So maybe next LCA, somebody can give a nice talk on transactional memory in Java languages. So let me talk about GCC. There's a whole little wiki page, so you don't have to actually believe all the stuff I said. There's a whole wiki page that describes how this all works. They've basically added 3 keywords and 2 attributes to the language. So there's transaction atomic, which says do everything in here atomically. The other one, which I'm actually not sure I'm a fan of, is something called transaction relaxed. So here's what happens. When I'm in a routine that's where I'm doing transactional stuff, if I call a function which is not transactionally safe, a good example is fwrite, right? I mean, for one thing, there's no way to roll that thing back. And for another, there's not a sort of transactional implementation of that. The compiler will barf and say, you can't call this non-transactional thing in your routine. Okay. But there's actually times where you might want to do that. And debugging is a really good example, right? I want to add a print statement. Even though I'm in transactional memory and I want all the right stuff to happen, I really do want to call printf because I'm going to dump a debug statement out there. So transaction relax says, all the sort of code that's in here, I want you to do transactionally. But if I call something that's not transactionally safe, by the way, exit, may surprise you to hear, is not transactionally safe. Okay? But there's certainly cases in my code, if pointer equals null, oh shit, I want to exit gracefully because something's really screwed up, where I want to say call exit. So transaction relaxed lets you do that. Well, that's, I don't know, I guess it's a good idea, but it means you're now, if you end up calling then some other routine of yours which is not transactional, which is going to touch the same data, which actually should be transactional, it's not. The compiler's like, yeah, whatever, you're good. But anyway, that's why that's there, is because there are too many cases where people in the middle of a transaction wanted to do exit or printf or whatever, and for in error cases. There's transaction cancel, which is kind of cool. It actually says, don't do anything we were just doing. So I've gone and modified a bunch of memory, and then I do transaction cancel. It's like, So it basically undoes everything and takes you to the bottom. Okay, that's mildly useful. And then 2 attributes you can add to functions. Transaction safe says, and there's some cool stuff behind the scenes going on here. Transaction safe says this function should be built so that it can be called within transactions. Right? So if I'm writing my insert node into a list routine, I'll mark that as transactionally safe. And then that means the other code that's in the transaction atomic, not relaxed version, can actually call that, and the compiler says, great, you're good to go. And then transaction pure is kind of a variation on that. A good example of transaction pure is something like a log function. Okay? I can call that thing all day. I don't need you, Mr. Compiler, to track what it was doing inside there. So it's transactionally pure. It's basically idempotent is kind of the correct term. I can call it all day, over and over. So I can run the transaction, call this function, go, oh crap, I have to roll back and rerun the transaction. I can call it again. Nobody cares. So you can mark transactions as transaction pure. And that's what that means. If you want to go look in the code, and I'll talk about the code as we go along here, within the GCC source tree, there is a transmem.c, which is about 5,300 lines of code. And transmem.h is really short. And then the runtime part, that's the part that generates the code. And then there's a library, libitm, which has a whole bunch of files in it, which is the runtime part that does all the work behind the scenes. So if we take a really simple function, so this thing is taking in a pointer to x, a pointer to y, transaction atomic, I'd like to add y to x. There we go. To make this all work, you have to be on GCC 4.7 or better, and you compile with the fgnu tm keyword. Awesome. If you start getting into playing with GCC, I don't know how many people are here have ever done the fdump options on GCC? Okay, like 3 or 4. So you can start to drill in. If you want to start understanding what GCC is doing, the very first place to do it is to start doing fdump. You can do fdump all, by the way, which is dump all sorts of debugging intermediate steps of GCC. This is what gets happened in the fdump tree tm lower, whatever, transactional memory lower. This is the intermediate stuff that comes out, and it's actually not, in this case, not terribly interesting. Calls transaction atomic, calls commit transaction at the bottom. So this is where we get hardcore. This is the assembly that's actually generated from that. And a couple of things. I come down here, I do a whole bunch of standard gorp at the beginning, messing around with the stack. And then I call itm begin transaction. That is a call to the libitm library, runtime library to do stuff. That's very straightforward. This is where things get a little more interesting, is like down here. So this is where the code is actually reading itm r unsigned 4. So read unsigned 4. So what I've actually done is it's actually, even to read that value, x, I don't just read it anymore. Sorry, that wouldn't work. I actually have to make a library call with all the overheads of branch misprediction and all the other crap to the library, say, please read me this memory. And then the runtime does that. So there's, let me tell you, non-trivial overhead. There's a big difference between, hey, I'd like to read this memory from this address space, and hey, I'd like to make this library call to do it for me. Anyway, a couple of calls to, and if I didn't want to make this go on too long, but farther down there will be an itmw where I write the results back. itmw argue for to write the results back. Okay, so that's what's happening behind the scenes. I pretty much all said all that, so we call libitm. And again, one of the cool things is there's a contract in libitm.h, which basically is what the compiler expects your runtime to do. And if I want to write my own runtime with different instrumentation or different algorithm or whatever, all I have to do is do LD library path, or LD preload, put my library ahead of the one that they expect, and then I can do all sorts of cool stuff with replacing the runtime, which is, I think, pretty cool. So that's my libitm can be replaced. The ABI is kind of standardized, and it's actually an Intel spec. So eventually, like I say, Intel did have a prototype compiler for this. It came out in 2010 or 11 or something. They've since withdrawn it, but since they're adding transactional memory support to their hardware in 2013, I finally suspect the Intel compiler will also have transactional memory support. So the ABI is the contract between the compiler and the runtime for the code that the compiler is actually going to make. Blah, blah, blah. I said the interface is in libitm.h. One of the sort of interesting things is the only library calls that are built into this are malloc free, memset, and memcompare. Okay? Malloc and free you have to make transactional, because inside a transaction I may do a malloc, and then all of a sudden I say, oops, I need to roll back the transaction, so all of a sudden I need to put the memory back because I didn't actually malloc it, I actually am redoing this transaction. Same thing with free. Okay? So they actually have transactional versions of malloc and free, which, again, for a free, defers the free until the transaction is committed, similar for malloc. And then memset and memcompare are the only other two things that are part of this contract with the compiler. The compiler is going to call your version of memset and memcompare. By the way, you need that because I'm going to blit values into a range of memory, and if I have to roll back the transaction, I better unblit the values into that area of memory. If they wanted to support more sort of built-in transactionally safe stuff, we're going to have to change both the compiler and the runtime library to add those. So if I did something like this, string compare, turns out, is not the same as mem compare. If I do this, in my function I want to string compare A and B, the compiler is going to barf out and say, I'm actually making an unsafe call. And this is where I would use something like transaction relaxed. It's up to you, the programmer, to figure out whether this is safe to not do transactionally in your code. Sometimes it is, sometimes it isn't, right? I mean, if I've put things into a tree and they're immutable essentially, then it's fine to call string compare all day, and the data is not going to change. On the other hand, if I'm actually mutating that data, then that would be a horribly unsafe thing to do within a transaction because I'm going to conflict with other threads. So I don't know. I consider this to be definitely use with care. If I'm writing a function and I want it to be callable from within a transaction, then in the header file for that function, I would declare that it's transaction safe. Okay, so now I can have the function over here in some object file called from some other file, and everybody agrees that it's transactionally safe to call that particular function. So I add an attribute to say it's transaction safe. What's really cute about that is that the compiler actually generates two versions of the function. It generates this is the standard version of what I just did. So I'm going to flip back, the same thing I did before, add y to x. This is the standard non-transactional version of that. It also creates a version with a horribly mangled name, which is the transactional version. And the compiler is now smart enough to say, if I'm calling this particular function not from within a transaction, then I'll call the cheap version that's not transactional. And if I'm calling this function from within a transaction, then I'll call the expensive version, which does all the wrapped functions. Okay, so under the covers, the compiler is generating two versions of every function, which is, I think, somewhat cute. Sir?
What about pointers to functions?
Pardon me?
Pointers to functions in this case.
Sorry, I still...
If I create a pointer to this function.
So yes, so the question is, what if I create a pointer to this function? That actually had to do with one of these patches I submitted to GCC because they were doing that wrong. So yes, if you were calling a pointer to a function, they've tried to do it right, but there were cases, and that's why I added a bunch of instrumentation and discovered that in fact they were calling the non-transactional one when they should have been calling the transactional one in certain situations, and it was generally kind of miserable. So that's actually a great question, and the answer is, in theory, the compiler will figure it out and do it right. This is a direct quote from the release notes for GCC 4.7. Several parts are not yet optimized, and if it performs really horribly badly, submit a bug or a patch, which would be even better than a bug. So it's, again, early days. The other thing is, I've mentioned I did submit some patches to GCC. I'd never gone and looked at the GCC source code before I started playing with the software transactional memory. And this is my view of GCC. I mean, GCC had to be there before the Linux kernel. Before Linux came along and started anything, we needed the GCC compiler. Okay? And it's actually been really cool. I mean, people use it for benchmarks all the time. It has for transport, language support. It's added a bunch of language keywords and structures that other compilers have picked up, so it seems really, really good. So as a user, it's really awesome. As a developer, once you start looking behind the walls, are there any GCC developers in the audience? I mean, the code is horrible. I mean, it's hideous. Because GCC is single-threaded, they're really not worried about squirreling away some piece of global state over here. And then you're in the middle of doing compilation and something triggers you to go look at, the state squirreled away over here and do something differently. And so you're trying to follow along what the code is doing, and anyway, not the prettiest code. Actually, it's really bad. So I'm going to digress for a little bit, because I've mentioned this a couple of times, and talk about the hardware support that's coming. So here's a really interesting thing about hardware. because we have multiprocessors, cache-coherent multiprocessors, the processors already have to keep track of who owns certain pieces of memory. And the same level of granularity you need for transactional memory. It's fine for 6 processors to all have the same copy of the memory that they're reading. It's really bad if one of the processors writes to that piece of memory and it's in the cache of all the other 5 processors and I have to invalidate the cache. So really the hardware already has to do a lot of what transactional memory already does. You already have to detect conflicting reads and writes. When you actually look at doing transactional memory in the hardware, one of the things it means is you're limited by the size of the cache. So you're really going to build your transactional memory hardware implementation on top of the existing cache stuff. And I think it's done in L2 cache level, I believe, in Intel. One of the super cute things, and these are the generic things. I'm going to talk about Intel and Power separately in a second, but it doesn't really matter whose hardware it is. Remember the case I said that you have a problem if you have this part of the code that carefully wraps your transaction in curly braces, and somewhere over here somebody reaches in and just pokes a piece of memory? Well, the nice thing about the hardware support is it'll handle that just fine, because within a transaction, it's just saying, did somebody else go and modify this piece of memory that I used earlier in the transaction? If it did, oh crap, we have a conflict, let's roll back. Okay? So it's better at handling code that's not correctly transactionally wrapped than the software support is. Probably not a good idea, I'm just saying it's better. There are some really interesting, and we'll see where this is going to go as the hardware rolls out. There are some really super interesting issues with doing transactional memory in hardware. Like, what happens if I do a syscall inside my transaction? Okay, the way the hardware does transactions is when I start a transaction, deep in the hardware, it actually squirrels away a copy of all the registers. Okay? And then if I roll the transaction back, it undoes all the cache changes and it restores the state of the registers. Well, what does the kernel do when I do a syscall? It squirrels away a copy of all the registers. But it doesn't, unless we make some changes, and actually the hardware doesn't support this today, it has no idea what the original, right, the before I do the transaction, the committed, if you will, copy of the registers. It only knows what the one is right now. So when I do a syscall, I believe what's going to happen, at least in the Intel support, when I do a syscall, I think I automatically invalidate my transaction, which means I can never do a transaction that involves a syscall. Okay? Same thing with interrupts. Exact same issue, right? I'm in the middle of a transaction. I take an interrupt. The kernel all of a sudden squirrels away, depending on what it has to do for the interrupt, but squirrels away a copy of all the registers, but it's not squirreling away the committed version, it's squirreling away the currently maybe ones we're going to roll back version. Debugger, same issue. How am I, so I set a breakpoint inside a transaction. I mean, anyway, may never, whatever. Context switches, same thing. And then the limited cache size. So it's possible if I'm relying solely on transactional memory hardware support that I can build a transaction that'll never complete because I actually touch more memory than will fit in my level 2 cache. Okay, so if I'm relying on the hardware, it'll just never happen. But so by the way, most of the hardware support I think is going to fall back on using a software transactional memory version if the hardware transactional memory doesn't work. So the GCC support I think is going to continue to have legs and be an important part of this. It's really going to be the hardware I think will be an optimization. But none of this has been implemented yet, so watch this space. So Intel is adding, they have this thing called transactional synchronization extensions. It's going to be in the Haswell architecture, which is supposed to come out in 2013. I talked about fact handles. I don't know why that second line's there. It handles the cases where something's not wrapped in a transaction. They've done something incredibly cool, and I'll sort of talk about it on the next slide, called hardware lock elision. And basically, it's transactional memory that behaves transactionally using only the existing locking primitives. So I'll talk about that. They also added what they call restricted transactional memory. This is the full-blown, they have an instruction called, this is the beginning of a transaction. They have an instruction called, this is the end of a transaction, and one called abort 5 minutes. Crap. There's a simulator available, and by the way, GCC 4.8 already has an -m RTM option, with GCC 4.8 hasn't come out yet, but what will be GCC 4.8 already has a keyword to support that. This is one of the coolest things ever. So they've added an instruction which is a prefix before an instruction called xacquire, one called xrelease, which you do before the unlock. And here's basically what it works. So normally, a lock, you flip a value from 0 to 1. Anybody else comes along, sees it's already 1, waits, or a few texts or whatever it is, till it goes back to 0 and then proceeds on. What they do is if the hardware supports this hardware lock collision, when you hit the lock, they say, this is the beginning of a transaction. They don't actually do anything. Then they let everything go forward and they treat the release, which is going from 1 to 0, as the unlock. If anywhere in that block, as long as nowhere in that block anybody else conflicts on their memory accesses, then they don't block either thread. So two threads can do a lock, a bunch of reads and writes, and an unlock. And as long as none of the memory that they touch conflicts, the processor says, you're good to go. So it doesn't block the second guy. It's this optimistic forward progress. And it's backward compatible because all I've done is add a prefix instruction to the lock and a prefix instruction to the unlock. Okay? So in my red-black tree case, I would add a lock at the top of the red-black tree. Two threads of execution could be poking around at the tree at the same time. I do an unlock when they're done, and as long as they never did conflicting memory access, they can both read the root node, read some other nodes. As long as they never write and conflict with each other, then they can actually run concurrently, which I think is freaking cool. And I think exploiting this both in the kernel and out of the kernel will be pretty interesting. If there is a conflict, it actually rolls you back to the lock thing and then treats it like a regular lock. Okay? So that's pretty cool. Doesn't exist yet. I'm sure there's going to be some interesting edge cases. Apparently, since I have now 2 minutes left, there's also their full transactional memory where they're added xbegin, xend, xabort. Xbegin as an instruction includes a pointer to a fallback function. So if the transaction aborts, leap to this code with a reason code. The reason code can be either user generated. I called abort used the called abort instruction within my transaction, or it can be hardware generated, just somebody else conflicted with my transaction, or I ran out of cache space or whatever. And then we could fall back on software transactional memory. Power 8 at IBM typically does more extensive architecting than other people do of many things. So they've added tbegin, tend,tabort. They also added tsuspend and tresume. And those give you access both to the register's committed state and the register's speculative state. So now I can actually start building things like debugger support or kernel support that squirrels away both the committed and the speculative state of the registers. That'll be interesting. They also, because ever since they introduced the EIEIO instruction into PowerPC, they've enjoyed their little jokes. So they've added a tdoomed status bit, which says this transaction, I happen to know this transaction is not going to commit. And then because everything's done in Austin, Texas, they have the transaction exception and status register. Anyway. Okay, last couple of slides. So this has all been a glorious thing. STM is great. It's the future. You guys should understand it. Lots of opportunity to contribute. How does it actually perform? So this is the red-black tree thing. And I'm just inserting a whole bunch of things in parallel to a red-black tree. One is using a spin lock around the whole tree. One is using mutexes around the whole tree. And then this is software transactional memory as the threads go up. Now initially, I ran this on my 4-core laptop. So I only had 4 cores of, and I should have done this earlier, but I was spending time on my animated red-black tree thing. But if you look at, so on my 4-core machine, I'm like, well, all right, all of a sudden, so mutexes don't do so well. And by the way, STM should do much better because I should be able to do some parallelism where the other guys are really only letting one person into the tree at a time. Mutexes kind of sucked. Spin locks start to suck. And then STM does this. So I'm like, oh my God, if only I had more cores. Clearly, STM is going to level out and do fabulous. And the other ones are going to go up, and I'll be able to walk in here and say, hallelujah, we have concurrency. So this is GCC 4.7. I thought, well, I'll try 4.8 and see if it's the same. By the way, this actually kind of really confirms my numbers because this was a completely different run generated with a completely different compiler, generated identical freaking results. So that made me think my results are okay. So then I went and stayed late at work and borrowed one of the work machines. I got up to 6 cores, and that was relatively useless. It didn't actually say anything. This did not say, software transactional memory makes my tree insertion work so much better. You guys should go buy one. Okay. So I can't walk in here right now and say it's the solution to concurrency problems. On the other hand, it didn't suck terribly, so that was good. It's not worse than doing locks, but it also, there wasn't a compelling reason to use it either. But once we get the hardware support, then, so it's like every hardware and software vendor since the beginning of time. It sucks now, but it's going to be great in the next release. Okay, so this is really kind of where we are with transactional memory. And fortunately, I have 1 minute left, and I'm on the conclusion slide. So I think you guys should really care. I think it is going to be very hot in the next couple of years. I think, especially some of that Intel support, I think, again, in glibc, in the kernel, I think there's going to be some really cool and interesting opportunities to take advantage of some of those instructions. And if you care, the slides are actually available. If you Google, you'll probably find them. So, that being said, and since we're at exactly question time, we have time for questions. If you have a question, put up your hand, and the microphone will come your way. Do you have any questions?
For the results at the end, did you have any numbers on the conflicts in the locking cases versus the rollbacks in the SCM cases?
No. So the question. Well, I don't repeat the question. One of the next things I want to do is do some instrumentation of the locking, instrumentation of the STM, dump that stuff out. I didn't get that done. It's clearly one of the next things I want to do, but. One of the things is I'm not even sure if we're getting gated by memory bandwidth. I mean, the fact that all 3 of those lines were so similar sort of makes me think that concurrency and processor power for insertion into a binary tree wasn't my issue. Memory bandwidth was probably the issue. So anyway, O profile, perf, adding some all sorts of things I need to do, but I haven't done that yet.
I noticed in all your examples you're using integrated types in GCC. How does it handle the type depth or a structure or something in the transactional model?
No, it handles it fine. So the question, how does it handle richer types? It's in both C++ as well as C, and it's really done at the bottom level. I mean, it's really done at the assembler generation level. It doesn't really matter what I'm doing. Though it does, the granularity is read and write a 4-byte thing. So if I'm writing a whole structure, it's going to chunk it up, dunk, 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 or maybe use memcopy. But it at the runtime level, it's doing it in 4-byte chunks. But it handles whatever types you want. Just as a sort of aside, it actually is smart enough to know that if there's a local, what I was doing in my examples was passing in a pointer to x, pointer to y, and adding them together, right? Those are visible outside this function. They need to be transactionally controlled. If I had just inside that function done int x equals 1, int y equals 2, z equals x plus y, it would have said, I don't need to do that transactionally because nobody else has visibility to those variables. So it wouldn't have wrapped those in the read and write calls. It just would have added them. So it is smart enough to only do things that are visible outside of my function.
For the syscalls, what you mentioned before, the limitations, would it actually make sense to try or want to have system calls be like work inside transactions? Because you're trying to change state that's outside of the process, like in the real world, so to speak.
Right. So for software transactional memory, done with the way it's implemented today, syscalls work just fine, interrupts work fine, context switches work fine, because we're not using the hardware for anything. It's all done in software. It's like the Wizard of Oz, the man, ignore the man behind the curtain. It's the hardware one where things are going to get cute. And as I said, power actually does expose both the committed and speculative state of the register. So I actually have the opportunity to perhaps grab both of those states as a kernel, squirrel them away, and then restore them when I return from a syscall. As long as the cache is still indicating there's no conflicts, my transaction can go on and I'm fine. Now the problem is you make a syscall, you're going to flush the crap out of the cache, and you may or may not, your stuff may or may not still be there, but it's certainly more possible. The Intel hardware, from what I've read the specification, the hardware's not there, though there is a simulator available, so in your spare time you can download the Haswell simulator and start playing with it. The Intel architecture, I don't think, gives you enough information to do that. I don't believe anybody could implement a syscall that preserves transactional state.
But I mean, like more like system calls that affect the real world, like say they do I/O or something. Does it make any sense there? Or?
Probably not. I mean, again, if I'm going to write to a disk, can't roll that back.
But things like get PID.
Get PID, get time of day. I mean,
Yeah.
So, right, those ones should be fine. I don't believe the hardware support's going to work. But again, maybe the trick is, for those ones, I just fall back on the software implementation.
Or we have these syscalls or something.
Do we have time for more, or are we done? You guys, one more question, according to the men in the blue shirt.
If it's smart enough to figure out that local variables don't need to be protected, is it also smart enough to figure out that a function whose entire body is in a transaction is itself transactional, that something that only takes or only has local parameters is
Yes, it's supposed to be.
pure, that sort of stuff?
It's supposed, so you can explicitly label a function transaction pure. And that's so I can do that, say, in the header file, so that the compiler at the compile time has no visibility into what that function does, but I'm just promising that this thing is pure and that I can call it over and over again. If in the same source file I have a function which is pure, I mean, adds x and y and returns, or a min function, clearly that's transactionally pure. The compiler is smart enough, it's supposed to be smart enough, I think it is smart enough to figure that in fact is pure and doesn't have to wrap that stuff in transactions. So yes, the compiler is generally smart enough to do that kind of thing the right way. Anyway, thank you very much for coming. I very much appreciate it. I'll be around all week.
Thank you very much for coming to our conference, and it was a very interesting talk. It's always good to hear about the new technology, so thank you again.